Hello, everyone. My name is Arije Dokas, and today I'll be presenting on the topic Machine Learning Foundations. Machine learning, by the way, it's one of the most important fields in artificial intelligence today because it allows computers to learn patterns from data and make decisions without being explicitly programmed. So in this presentation, I'll introduce the basics of machine learning, the model types, common algorithms, and finally, I'll present a real-world problem where machine learning can be applied using acoustics. So machine learning is the field of study that gives computers the ability to learn automatically from experience. Instead of writing rules manually, we provide the machine with data and it discovers patterns that help it make predictions or decisions. For example, instead of now programming a system with rules to detect spam emails, we train it using examples of spam and non-spam messages. Machine learning is mainly divided into two types. We have the supervised machine learning, whereby this is when the model learns from a labeled data. For example, predicting whether an email is spam or not. Then we have the unsupervised machine learning. This is when the model works with unlabeled data and tries to discover hidden structures, maybe such as grouping similar students or customers. Then next we look at the model types. A model is basically a mathematical representation of a real-world phenomenon. And we have two main types. We have the deterministic, whereby these ones have no randomness. They assume that if we know the inputs, we can predict the exact output. For example, maybe like in physics, if you drop an object, it will fall with a predictable acceleration. Then probabilistic model. These involve randomness and uncertainty. Most real-world problems are probabilistic because data is noisy. For example, maybe let's say predicting a student performance is uncertain because many factors influence it. Then next, let's look at the parametric versus the non-parametric models. Models can also be categorized as parametric or non-parametric. So parametric models, in a parametric model, we assume the shape of the function before training it. A good example is linear regression, where we assume the relationship is a straight line. Here we use the equation of y equals wx plus a. This model is simple and works well when data follows in a linear pattern. Then we have the non-parametric model. In a non-parametric model, here we don't assume the shape. The data itself determines the function. And we shall use the equation of y equals fx plus e. These models are more flexible and can capture the complex patterns. Then next, we look at the IRIS dataset and the KNN algorithm. One classic dataset used in machine learning is the IRIS dataset. It contains flowers from 3 species, and each flower is described using 4 measurements. This is the sepal length in centimeters, sepal width in centimeters, petal length in centimeters, petal width in centimeters. Here the goal is to classify the flower into the correct species. The popular algorithm used here is the k-nearest neighbors, or the KNN. Then next, we talk about the main steps of the KNN. KNN is a simple classification algorithm. The steps include calculating the distance between all the training data and the test point, finding the nearest k-neighbors by sorting these pairwise distances, classifying the point based on majority vote. For example, if most of the nearest neighbors are Iris setosa, then the next flower is classified as Iris setosa. Then we talk about the KNN distance matrix. KNN mostly depends heavily on distance measures. Here we talk about the Euclidean distance, which is used when features measure the similar properties. Then we have the Manhattan distance. This one is used when dimensions are different. Also, features must be normalized if they are on different scales. Then applications of the KNN include the text mining, agriculture, and finance. The decision tree pruning and matrix. A decision tree splits data into branches based on the feature values. To measure split quality, here we shall use the Gini impurity. Gini impurity, it measures how often an element would be misclassified. Then when we talk about entropy, it measures the disorder using the logarithms. Gini is faster to compute, while entropy is more complex. Let's talk about the random forest. A random forest is an ensemble for many decision trees, and it works by, it takes the random samples of data using bootstrapping. It randomly selects features at each splint, then also building multiple trees and averaging results. Then building the multiple trees and averaging results, this reduces overfitting and improves the accuracy. Ensemble learning. Ensemble learning means combining many weak models into a strong super model. Then we have just two key types, two key methods. We have the bagging and the boosting. The boosting mainly it emphasizes the sequential tree growing with weighted samples. Then for bagging, it is a parallel tree growing with subsamples. Random forests are an example of bagging. Next, we have the k-means clustering. K-means is one of the most popular unsupervised clustering algorithms. Here, we look at the strength and the weaknesses. The strength here, it is simple and efficient. It is easy to understand. It is even more popular. Then for the weaknesses, we see it is sensitive to the outliers. It depends on the initial seeds. It doesn't work well for non-spherical clusters. Then we have the support vector machine, the SVM. SVM is a powerful classification algorithm, and it gives more weight to correct classification than the margin maximization. And it can also detect the outliers. Then we have the Kernel function, which defines the inner products in the transformed space. Then we have the gamma, which is which controls how far a single point influences others. The low values of gamma indicate a large similarity radius, which results in more points being grouped. Then we have the principal component analysis. PCA, it is used for dimensionality reduction. Then it reduces the number of features while keeping most of the information. It works best when variables are linearly correlated. PCA performs lossy compression, meaning some information has to be lost. Then next, we look at now the problem statement. This section mostly focuses on applying the machine learning using the acoustics. And now we are going to include we are going to follow the criteria of what is the problem, why is it a problem, to whom is it a problem, to what extent is it a problem, and how can it be solved. So what is a problem? Here we had to consider the issue of class attention monitoring using acoustics, and it relies heavily on visual observation, which is limited. So the problem here, it involves inability to know how many students are engaged in real time, difficult to detect lack of attention. Then we have one teacher can't monitor very many students simultaneously. Here we are talking about very large classrooms. Then why is it a problem? This is important because attention directly affects the learning outcomes. So without feedback, teachers cannot adjust teaching methods in real time. Educational resources are wasted when students are disengaged. Then who is affected? This is to whom is it a problem? Here we shall be looking at the teachers, students, parents and guardians, and the educational institutions. Then to what extent is it a problem? The effect includes lower exam scores and academic achievement, increased dropout rates, teachers spending a big percentage of time on behavior management rather than instructing. Then how we can solve this problem? We can solve this by analyzing the acoustic signals such as the speech patterns, student responses, background noise, the silence patterns, and the dynamics. These features can indicate engagement or distraction. Then if we can see the applicable machine learning algorithms, these are the machine learning algorithms that can help to deal with these problems. We have the KNN, or the K nearest neighbors. Then for it is based on attention. Then we have the decision trees or the random forest. This will handle the nonlinear acoustic patterns. Then we have the support vector machine. This is effective for high dimensional acoustic feature spaces. Then we have the principal component analysis. This will reduce the dimensionality of acoustic features while preserving violence. So thank you for listening. We shall stop from here.